So we have another update today on our research in artificial general intelligence. So for background, we're building an AI that can take in a description of a problem in natural language, build an internal model of that problem, try to solve the problem, and using feedback, experimentation, and testing, try to refine its solutions to the problem if necessary. And to do this on a more technical note, what we're looking for is an AI with the ability to make an internal model or an internal representation of both the solution and the given problem that can be defined, updated, and expanded upon with natural language descriptions, can be refined through observation and watching through examples, can be refined through its own experimentation and testing, and can be refined through basic reasoning and breaking down a given harder problem into smaller subproblems. And in this previous update, we've demonstrated a proof of concept with an ILM, or an intermediary language model. That is a model that bridges the gap between language and something we call a meta model, which is this glue model that bridges together different aspects of problem solving. So in this demo, what we're looking at is checkers, specifically having an AI build and render its own representation of a checkers board. Not quite yet playing that, that's coming in a future video. And I should clarify that there's a difference between the AI itself and the models it uses. So the AI builds models for a problem, but the AI itself is not the model that runs the problem. So the AI here is used to build and run a model of checkers, but the exact same AI can be used to play tic-tac-toe or do some other task. And in the intermediary kind of model, the way we represent processes and change on states is through a decision engine. So just to clarify, this is a previous model we've run with tic-tac-toe. And we can run this and it'll go through and play a game of tic-tac-toe, and it'll try to play it strategically so that one side can win. In this case, it plays against itself and then it ties. So our current update is effectively the meta model has gone into the point where it can understand actual complex tasks, conditional logic, and iterating and recursion. That's the biggest thing. And the importance of the meta model is that it provides us kind of like this binding substrate that we can then attach a language model to, which is also being researched on. And the language model is running using this exact same type of AI that, that just play tic-tac-toe. So hence, this is a very generalized type of AI. So for instance, the first thing you do is say, okay, how do you set up a board? So when we're talking about checkers, normally you say, okay, you're playing an AI in chess. So the programmer wrote the AI logic or wrote the chess logic just by themselves, and then only asked the AI to solve it. But most of the logic is done by the programmer. Here, the AI does everything. It manages the internal state. It manages determining how to render it to a screen, stuff like that. So if we look at, say, the setup board directive, we can run that, and it doesn't show anything because all it's doing is just setting up a board. It's not even printing it yet. And then we can actually look, what it's doing is setting up an internal representation, which is saved to a database of all the tiles involved. As you can see, it says, okay, for each tile, it's got, row number, column number, piece, B for black, R for red, and then some information like, okay, is this a light tile or dark tiles? Checkers from chessboards, they alternate white, black, white, black, white, black tiles. Or squares. And then there are 64 tiles, starting counting from 0. The other cool thing is it's not hard-coded to a given size. So there's something called a checkers board size that's set to 8, but you can create a board that says, okay, 9 or whatever. This information is now stored inside the AI when it runs. So if you say, okay, I'm going to make a checkers board 9, not only can you have it build a board that's 9 by 9, but the AI, when it's planning out moves, will take that into account. Which for checkers doesn't make a whole lot of sense, but if you're playing like chess, it does matter, the size of the board. So then we have a second sub-model, which is render board, and this says, okay, how do you take that internal model and then display that to screen? So this is very, very linear kind of logic, but it's one part of a much broader base. So you're gonna have how do you make a decision moves? With checkers, because if you can take a piece, you have to take a piece on your turn. So you have this kind of extra layer of logic. So it's not as simple. When I was running tic-tac-toe, the logic's very simple. You can pick any move that hasn't been picked yet and just go. But this actually requires the AI to be able to recursively think, okay, I'm going to pick a set of moves, but first I have to list out what possible moves are. And then if any one move can take a piece, then I have to filter out all the moves in my possible list of moves that can take a piece and then choose from one of those. It's a very fun kind of problem. And this obviously, if the pieces move around, the board will render. So that's pretty much it for now. So we're now working on like actual like the next step is playing checkers and then demonstrating. Okay, how do you take a naive objective? So a simple naive objective is like remove all the enemy's pieces, and then break that down into sub steps, so that I can say, oh, okay, I can reason out. Okay, the player currently has 30 pieces. The end objective is 0 pieces. So an intermediate state is any piece is 1 piece less. So anything I do that removes a piece is good. So then you create a sub objective. You say, okay, I can't find any move that wins the game out of the bat. I mean, you can't beat checkers in one move. But what you can do is say, okay, if I know that the enemy has 27 pieces or 24 pieces starting, and the end goal is 0 pieces, and I can take 1 piece at a time, then any move that can remove a piece, say 24 to 23, that in general most likely is going to be a better solution to get me to the end. So then it says, okay, well, what can I do to force the enemy to drop a piece? So that's actually my next set of work, and it's using something called characteristic engine, where we write the code into the decision engine using something called characteristics. So the AI doesn't have to worry about like when it's creating the decision engine can run iterations, it can run recursion. But when you have AIs try to write code, you run the risk of, okay, well, it writes an infinite loop or something silly. What instead we do is we write characteristics, which use information about the problem at hand with regular code, a human would write, and then turns that into stuff. And then we can, as a human, because I wrote the code, I can say, okay, make sure, you're not doing infinite loops or getting stuck or doing something weird like referencing objects that don't exist. And for a quick like demo of like what that kind of information looks like, if we go down here, so for instance, setting up a board, we break these, setting up a board into sub steps, and then each one of these actions, says, okay, how do you filter and identify, like how do you iterate over a given row, stuff like that. So this is of course obviously written by me. Obviously the idea is like we use the meta model with the ILM to set this up. So when you see stuff like this will be machine generated. So it'll, instead of saying something I wrote like meta iterator, it'll be like A74-6, and the AI will know, okay, that means something it doing with the iteration task. Actually, meta iterators hard coded, but like this specifically, how do you filter over iterating over rows and columns? That will have like its own machine generated nonsense, and then the AI will then link that to, oh yeah, the user told me this means iterate over rows and columns. So when you ask the AI, okay, why did you do this? It would say, okay, A7-56 turns out into the phrase iterate over rows and columns.